Hi you guys, and happy first Friday. Today we are going to be doing our 1.2 functions notes for our honors breakout course. I'm hoping that this section of notes is just going to be a good refresher for us to kind of begin diving into the rest of the school year. But we're going to be talking about relations, functions, domain and range, and digging into some parts of piecewise functions, and hopefully getting a little bit of a refresher on some of our basics functions from Algebra 2. So here we go. A relation is when we have an everyday phenomena that involves two quantities that are related to each other by some rule of a correspondence. So some way these two are related, it's some kind of pattern that is making them get related. Now from a relation, then we can determine if something is a function. So whenever we have a graph, it's always normally a relation, but we could determine if it's a function if we have one element in our x for every one in our y. So that means that our x's only go to one y. X never goes to two different y values, so you should only have each x value listed once. Domain, you've been doing this since Algebra 1. Those are your inputs. So your x values is your domain, and then your range, those are your outputs, that's your y. Piecewise functions, piecewise, it's kind of how it sounds. It's pieces of different graphs on one graph. So it can be two or more equations that are specified over specific domains in your graph. So just pieced along that graph. A couple of parts that I want you to fill in. I'm just going to say the words. You fill them in on your own notes so that you know what we're talking about when we get there. What's a function? Well, we talk about it. It means each x goes to only one y. You know what? I will fill it out. Each x goes to only one y value. Okay, so that means that something like this would be a function. This is a function. When we have something sideways, this is not a function because these x values here would have been repeated, so this is not a function. Let's make these red so we can see that. Anybody remember what that specific test is that we used to use way back in Algebra 1? It's your vertical line test. So your functions pass the vertical line test. You could also call it your pencil test. Some of you used to call it that as well. All right. When is a function undefined? There's actually two times that a function could be undefined. The first one is going to be if you have a denominator equal to 0. So anytime that you have a fraction, if this bottom part is equal to 0 at any point, it's not going to be a function. It's going to be it would be a function, but it's going to be undefined at a specific value. So you're going to have to determine what that value is. Other time that we have an undefined function or a function that's undefined is when we have a negative in the square root. So underneath your radical, you would have a square root. Maybe I should say that. Negative under the radical. Okay? It's got to be greater than or equal to 0. You can have a radical that's equal to 0, right? But you can't have a negative number that's inside of that radical. So we would need it to be greater than or equal to 0. So let's kind of dig into these functions and start determining what their domains would be based off of those undefined portions that we need to leave out. Okay, so here's our first example. We've got 5x over the square root of x minus 3. Well, we've got two things here. We can't have the square root of x minus 3 equal to 0. We cannot have that, so I'm going to put a line through that equal sign, because then our denominator would be equal to 0. We know that's undefined. That's back from Algebra 1. Other part, we cannot have x minus 3 being less than or equal to 0, so it has to be greater than or equal to 0. Okay, so two parts that we're going to have to solve here, and you're going to see here in a second that one of them kind of cancels out the other. So if I solve these pieces and I square both sides of this, that's going to tell me that x minus 3 cannot equal 0, meaning that x cannot equal 3. Okay, and then my next part, I would add 3 to both sides, meaning that x has to be greater than or equal to 3. Well, this says it can't be equal to 3. That outdoes this equal part, so we got to take that part off. So we now know that x has to be greater than 3. This is our set in stone part right there. So x has to be greater than 3. Well, how can you write that for your domain? Well, we need to start with D, or you can write out the word domain and your colon. And then I either want you to write it in set notation, so you could write it just with your parentheses. We can start at 3, and because it's greater than, we go to infinity. Can't ever equal infinity, so make sure you use your parentheses. If this had an equal to, we would use brackets, so remember those rules. You might want to look over that. We can also use our inequality notation. More often than not, we're going to be using our set notation though. So I would prefer for you to get used to putting it like this. All right, moving on to the second problem for our domains. We are looking at a fraction here. It's got a denominator. We've got to look at where this denominator cannot be equal to 0. If we solve this, we've got x squared cannot be equal to negative 2. Well, is it actually even possible for x squared to ever be negative 2? Not in any of the real numbers in the world, no, because we can't make any number squared be negative. So this is actually just going to be our domain is all real numbers. We can't include imaginary numbers when we're talking about domain. All right, third problem for our domain here. We are looking at another fraction. Don't have to worry about anything happening in the numerator. Just paying attention to this denominator. We cannot have it be equal to 0, so we need to think about this. This is a quadratic. You should be real quick at solving these quadratics, okay? So we know that if you got a quadratic, you might want to factor it. There's other ways that you could simplify this if you don't know if you've got a perfect factor in there. So think back to those ways that we solve quadratics. This one is easily factorable, something that multiplies to negative 3 and adds to positive 2. That's going to be a positive 3 and a negative 1. Okay, so we're looking at two factors there, and neither of them can be equal to 0, which means we're going to separate them here. X plus 3 cannot be equal to 0, and x minus 1 cannot be equal to 0, leaving us with we can't have x equal to negative 3, and we can't have x be equal to positive 1. So using that, we're going to have to use our set notation for our domain. And we now have two values that can't be included. So we're going to have to use a little bit of our unions here and tell the specific areas of our graph where this would work. So if we think about our number line, if you still need to draw your number line, that's okay. We're not going to be here at negative 3. We're not going to be here at 1. So these would be our open circles. Everything else would be included on our graph. So we just want to restrict those two specific values. So we're going to go here on our domain from negative infinity to negative 3. Negative 3 is not included, so use those parentheses. Union, negative 3 to 1. Union means and, 1 to infinity. Okay, so that is our domain for that third example. Moving right along to number 3, you should be able to read a graph very quickly and determine points on a line. So here we go. We've got our g of 3. So looking here, this value would be like g of x. So that 3 is our x component. So I'm going to go over to my 3 on my x-axis here and go up on my graph to where that point is. So that value for my y is 1. That's all I need you to figure out, is where that falls on your graph. F of 1. Now I'm looking at my f graph, figuring out this x value of 1 and figuring out where that is on my f function. So it is up at 4, so we're going to put 4. Next we have negative 2 on that f function, going to negative 2, and then I am here when I'm on my f. So that is at negative 1. And then lastly, I switched it up a little bit. Another way for me to say y is f of x, or g of x, or h of x, anything of x. This just means that y equals 3, right? So on my g function, we're looking specifically at g, where is y equal to 3? Well, my y is right here. So on my g, that point is here, and that is my x of 4. Second page, number 3. If we're evaluating the following, f of 2, that just means I want you to plug in value of 2 for our f function minus g of 2. I'm going to plug in 2 for my g function, and then I'm going to do that operation of subtraction in between. So I'm going to go ahead and plug in separately. I'm going to do f of 2. That is 2 squared minus 1. 2 squared is 4 minus 1 is 3. My g function is going to be g of 2 as well. 2 plus 1 is also 3. So when I plug those back into this operation here, I've got 3 minus 3. Well, we know that's 0. Okay, part B, a little bit more intense, but you should know how to do this pretty quickly as well. Anytime that I replace those parentheses, we're replacing x. So anytime that I see x in my function, what I'm going to do is I'm going to plug in. So right now, f of x plus 3 is now changing my f of x function. So I'm going to continue writing everything that was there, but replacing x. So now x is x plus 3. X is x plus 3. Okay, we need to simplify. You have got to simplify. So I'm going to start off with distributing negative 2 into those parentheses. Still got that 1 in front, minus 2x minus 6. I'm going to go ahead and square this. Remember that that's just us foiling, if you want to, on the side. But I know at this point that that is x squared plus 6x plus 9. Remember those rules of squaring a binomial. Last step that I need to do to simplify this part before I combine my like terms is distribute that 3. Still got all of this stuff, but now I have 3x squared minus 18x plus 27. Okay, combine those like terms, and I'm also going to go ahead and write it in degree order. X plus 3 equals, we've got 3x squared first, got that out there. I'm going to put my x next. That should be a positive there, my bad, you guys. That is going to be a plus 16x. And then our last component is going to also be our plain numbers. I've got a positive 1 minus 6, that's negative 5, plus that, so that is going to be plus 22. That is your simplified quadratic after we plugged in x plus 3. All right, number 4. Number 4. This one gets a little bit hairy when we get to part E for writing the piecewise, but other than that, we should be fine. F of 0, again, that's just where our function is equal to 0, so our x value at 0, that's equal to negative 2. At 2, our function is right here, okay? Well, we have a value that's an open circle, which means it's not included, and then we've got a plain line intersecting. Now, if you see a line, that means all those points on that line are closed, okay? I don't have to put these endpoints showing that they're closed. If I don't want to, it's assumed that they're included. The only time you have to put endpoints is if you're saying something is not included. So anytime there's an open circle, that has to be shown. Anytime there's not a circle at all, we're assuming that it's included. So the only point included for our x value of 2 is up here at 1. All right, our domain, that's all of our x values. All of our x values. So from left to right, we start at negative 3. That is included, so I'm going to use my bracket. And we continue. We do have an open circle at 2, but it's included on the other part of our function, so that is still an included value. And we go all the way to 5, which is assumed included, so we're going to close that with a bracket. Range, if you want to hear my trick, I say that Drake has a really awesome range. I know that's a lie, because he started from the bottom. Now we're here. So start from the bottom of your graph. We're hitting at negative 4. We're assuming it's included based on the fact that there is not an open circle there. So we've got our bracket, and then the top of our graph started from the bottom. Now we're here is at positive 4. So we're going to go to 4. It's a closed circle, so we're going to use our bracket. Now I'm asking you to write the piecewise for this graph. Now it says it's function of f, so let's just write it as f of x equals, and when we start a piecewise, you want to make sure you have that curly bracket. Okay, the easiest part of this graph right now is for me to do this line. We know that it is at 1. So we've got it from 1. And then the domain, you have to tell me where it is on our graph for this piecewise. Okay, so we're going to go from our starting point here of 2 to 5. And we're going to write that as an inequality. You can write it as a set notation. We're going to stick with inequality until maybe a little bit later if we ever decide we think that set notation is just better. But you're going to use those inequality notation, and because of those closed circles or our assumed closed circles on that line, we've got to include our equal to sign. Now the next part, this is actually an absolute value graph, okay? Absolute value graph, if you guys remember, is basically me including a negative slope line and a positive slope line all in one. So if I move over to Desmos here real quick, let me open up my Desmos, and I do my absolute value graph, absolute value of x. There you have it, okay? You have a slope of 1 in your parent function of the absolute value of x. Now, if we go back to this problem here, our slope is not 1. I'm going up 2 over 1. So we actually have a slope that's 2. Now, something that we need to remember is that if I have a 2 on the outside or a 2 on the inside, whoop, that's the same thing, of my absolute value sign, it's going to do the exact same thing. See how those lines are both overlapping right now? Going to mean the same thing. Now, if I have a shift, though, if I have a horizontal shift, these two graphs are not the same thing. So I'm going to prefer for you, if we have a change in our slope, to do that on the outside of your graph so that we're not to change our shifts. So here we go. Our parent function is normally at 0, 0. We know we now have a stretch of 2 based on our slope, absolute value of x. We have gone right 1 from our parent function, down 4. Right is always minus. So minus 1, close that absolute value, and then minus 4 for our vertical shift. And then we need to put our little colon saying where this is going on. So it's happening from -3, that's included, so less than or equal to x, which is less than, not included this time because of that open circle, to 2. So you could graph that piecewise function in Desmos, you could check it and make sure that you've got it correct, but be sure to refresh your memory on those absolute value graphs if you need to. Moving on to number 5. Finding when f of x, wherever our x is, from a piecewise function, okay? So we've got f of 2. All right, well, we need to know how to read this first. So just make sure that wherever you're looking for that x value, it's actually included. You've got 2 listed twice. 2 is not included in this second equation because it's not got an equal to sign. So make sure you're cautious of where it's actually included. So 2 is included in my x squared minus 3. So I'm going to plug in 2 squared minus 3. 2 squared is 4 minus 3 is 1. So f of 2 is equal to 1. F of 3 is also included in that third equation. 3 squared is 9 minus 3 is 6. Okay, now our next thing that we need to check is when f of x is equal to 3. So that's when our y is equal to 3. So something that I want you to make sure you add is a little favorites, and add just a coordinate plane so that you can quickly insert a coordinate plane into your notes or your practice. Since you will have book work, I'm not providing you with a worksheet. Make sure that you have something quickly that you can add in. So if we start graphing these equations, I'm going to do them in different colors. So this top one is just a linear equation. I'm just going to graph the whole thing first, and then I'll restrict the domain. We've got a y-intercept of 5, a slope of 2. I'm going to go down 2, back 1. Slope is positive, so make sure your line looks like it's increasing. So here we are, okay? And it's where all of our x values are less than -1. Not less than or equal to, but less than. So that means I need to put an open circle there at my -1 and then connect my points. And it's less than, continues on, so put an arrow. Next, we've got our f of x equal to -2 from -1 to +2. So down here at -2, I'm going to put my closed circle for -1, and it's continuing on through 2 with an open circle. And then last, we've got a quadratic. Our quadratic is shifted down 3. So if you were to just think about your quadratic and doing your parent function of that, down 3 would be here. And remember our pattern, we go up 1 over 1, and then we would go out another 1, up 3, out another 1, up 1, 2, 3, 4, 5. So you should have that ingrained in your mind as well, or just make sure you can plug in your points. Okay, and that is going from 2, and it's included, so that's a point, to 3, also included, and then connect those. All right, so where f of x is equal to 3, so where our equation, our y value, is equal to 3, that would be right in here. So that's going to actually be on our third graph. That's the only time it's included. So we've got x squared minus 3 equals 3. We're going to add 3 to both sides. That is x squared equal to 6. So x is equal to the positive value of the square root of 6 based off of where our graph is. Okay, so that is x is equal to the square root of 6. Last two parts is our domain and range. Your domain you could do from just your piecewise function itself, not really needing to look at the graph. We know that our domain is going from -infinity. And we continue on because we include -1 in the second part. We include 2 in our third graph. And we end our graph at 3, which is included and equal to. Last is our range. Our range is going from -infinity to our last value in our quadratic equation. So 3 squared is 9 minus 3 is a height of 6, and that is also included. So that is our range. You guys have a practice assignment to do. Let me know if you have any questions. I'd love to help you. Have a great Friday.